We have so far in this chapter focused on the case of conservation of mechanical energy. And as you know, the condition is that all the forces that did work must be conservative. But what if a non-conservative force is present and it did work? What's going to happen? Well, clearly, there's no condition for the conservation of mechanical energy anymore. So therefore, you don't expect the mechanical energy to be conserved. Therefore, you expect to change. But how much change is there? Well, to answer this question, we go back to the work energy theorem. We can always revert to the work energy theorem because that's just consistent with Newton's second law. Now, as you know, the idea was in the beginning of this chapter to rewrite the work done by the conservative force as the potential energy spent by the system. Okay, whereas with a non-conservative force, you cannot express its work to be the difference between initial and final potential energy. So naturally, what we want to do here is to separate the work done by these two forces into two separate terms. The first term is the work done by the conservative force, and the second is the term of the work done by non-conservative force. Okay, so here is the work done by the conservative force. And we know for this particular force, for this particular work, I know I can write this as U initial minus U final, and that can be written as negative delta U. Okay, delta U is U final minus U initial. So U initial minus U final is the negative value of that. But the work done by the non-conservative force, such as friction and so on, you cannot introduce potential energy. We just leave it as is. Okay, so now we're going to plug in these two terms, the work done by the conservative and the non-conservative force, into the work energy theorem. So then we have negative delta U plus the work done by the non-conservative force, NC, and that equals delta K, right? So I'm going to move delta K. I'm going to move this negative delta U to the other side. Then I get W non-conservative equals to delta K plus delta U. Now, as you know, this is just delta E. So you see, the mechanical energy E is no longer conserved because delta E is not equal to 0. Rather, it is equal to the work done by the non-conservative force. So clearly, as a special case, if the work done by the non-conservative force is 0, then delta E is equal to 0. So that is the condition for the conservation of mechanical energy. But now we have a more general formula that delta E equals to W non-conservative. Okay, so this is the formula that allows us to rewrite the work energy theorem in the presence of a non-conservative force. Okay, that did work. Okay, it's equivalent to work energy theorem, unlike the conservation of energy, which is just a special case of the work energy theorem. This version, the one that's boxed, is identical to the work energy theorem. The only thing we did, like I said, was to separate the work done by the conservative and a non-conservative force. Okay, so you don't have to worry about the work done by the conservative force because that's part of delta E, but for the work done by the non-conservative force, you still have to work it out. Okay, so the non-conservative force, when it does work, it will change the mechanical energy. So that's the basic idea. That's how we rewrite the work energy theorem. Now we're going to put it to use. Let's look at this example. So we have here a block sliding frictionlessly down a quarter circle track of radius r, okay, and it reaches the bottom of the track, and then it's moving along a horizontal stretch. It starts out at point B, moving towards point C, and between point B and point C, there is some friction, okay? This is point B, and this is point C. Between these 2 points, there is a stretch of the horizontal table that has a friction. The length is L, and the coefficient of kinetic friction is mu of K. Then it keeps on going afterwards frictionlessly, and it starts to compress the spring. It compresses the spring by an amount X. Okay, now we know exactly how to do this problem if there is no friction between B and C, right? Because energy is always conserved. We start out with only potential energy, gravitational potential energy. Then it all turns into kinetic energy. And then when it compresses the spring, all the kinetic energy will eventually turn into elastic potential energy, right? So you can write the conservation of energy throughout the entire process. But now between B and C, there is friction, and obviously it did negative work as the block moves from B to C. So therefore, we no longer have conservation of energy once it enters the stretch between B and C. Okay, now we can still find VB, VC, and the amount of compression of the spring. Between the initial launch point, point A, and point B, there is no non-conservative force doing work. Okay, I mean there are only two forces. You have gravity, you have normal force, and clearly normal force doesn't do any work because again it's always perpendicular to the direction of motion. So I do have EA equals EB. Okay, that I can still write. And if you use the ground level, the table level as the 0 point of the gravitational potential energy, then the initial potential energy is mgr because the initial position of the block is distance r above the final position, which is point B. So I have mgr, in fact. That is the initial potential energy. The initial kinetic energy is 0 if I start the block from rest. And when it reaches point B, it only has kinetic energy left that's 1/2 mvv squared. And that easily tells you what VB is. Okay, very simple to do. Now, between VB and VC, there is a friction, and it does negative work, so you don't have conservation of energy. You can still use the work energy theorem connecting B and C, but now we're going to use this slightly different version. We're going to use delta E. So here is A to B, okay? Now from B to C. Delta E equals W non-conservative. Let's see how that works out. Okay, delta E is EC minus EB, the change in mechanical energy. And you notice that since B and C are at the same horizontal level, there is no change in potential energy, the gravitational potential energy. So the only thing that changed is the kinetic energy. So we have 1/2 mvc squared minus 1/2 mvb squared equals what? Equals to the work done by the non-conservative force, which is friction. And that is from B to C, the work kinetic friction Fk dot dr. Now Fk is a constant. It doesn't change between B and C. So I can then rewrite this as just Fk, the magnitude, times the displacement L. Okay, Fk is along the direction, along the displacement L, except its opposite direction of motion. So Fk and dr, the angle between them is 180 degrees. So you have a negative sign. Cosine 180 equals -1. So you have a negative sign. Clearly, that's because the work done by friction is negative. It slows down the block. Okay, so Vc is going to be less than Vb. Right? Now from C to the final spot when it's fully when the thing is when the spring is fully compressed at point D, so C to D. You still again have conservation of energy because there's no more friction at work. So I start so you have EC equals ED, right? And EC is only kinetic. You have 1/2 mvc squared, right? And ED is purely elastic potential energy. That is 1/2 kx squared. So that tells you what x is, right? So that is how we treat a problem which involves the work done by a non-conservative force. Just to rewrite the work energy theorem a little bit to so you can focus only on the work done by the non-conservative force. I mean, the work done by the conservative force is part of the change in mechanical energy. Okay, so that's how we do this problem. I mean, if you want to solve it, you can easily find VB and then VC and then the amount of compression. Now, you don't have to go from A to B, then B to C, then C to D. You can go direct from A to D, the first state and the final state. You can do that. Okay, and if you do so, let's go from A to D, see how that works. Okay, And if you do so, you find that EA and ED, they're not equal. Because going from A to D, somebody did work. The friction did work, and it's non-conservative. So you can only write delta E equals W and C. You cannot write delta E equals 0. Okay, but we can then write down delta E as the final energy, which is purely potential, 1/2 kx squared, minus the initial energy, which is also purely potential, but it's gravitational potential energy, is mgr. Okay, mgr. And that equals the work done by the non-conservative force, which is negative Fk times F. So you can bypass point B and point C. You can go directly from point A to point D. That's not a problem. And you can see what we get here will be consistent with the three equations the three equations that we got. I mean, we have three equations here, right? In the previous method, we have equation number 1, we have equation number 2, and we have equation number 3. But here we only have one last equation, equation number 4. But equation number 4, you can solve for x from equation number 4. It will be consistent with the three equations that you have before, 1 through 3. You can easily see that because look, in equation number 3, we found 1/2 mvc squared to be equal to 1/2 kx squared. And here in equation number 4, you find 1/2 kx squared to be the sum of mgr and negative fkl. Now, in equation number 2, you see negative fkl is the difference between 1/2 mvc squared and 1/2 mvb squared, and mvb squared itself is equal to mgr. So let me write down what I just said. You can see whether you get a consistent result. Okay, it's quite simple algebra. So we have 1/2 kx squared so 1/2 kx squared equals to the sum of mgr and negative fkl, right? But mgr, as you can see from equation number 1, isn't that just equal to 1/2 mvb squared, right? And then minus fkl, but fkl isn't that equal to the sum of 1/2 mvc squared and negative 1/2 mvb squared from equation number 2, right? So I can write this as 1/2 mvc squared minus 1/2 mvb squared, right? Now you cross out 1/2 mvb squared and 1/2 mvb squared. What do you have? You have 1/2 kx squared equals 1/2 mvc squared, but isn't that the same as equation number 3, right? So from equation number 4, we get a result which is consistent with equation number 3. So no matter how you do it, you get the same final value for the amount of compression x. So this is a rather simple problem, but it does add the consideration of the work done by non-conservative force. Now I can go back and we can re-examine the problems that we did before, like this problem, for example. I mean, I can add some friction here, right? I can add a stretch with friction. How does that change the problem? Well, if you're looking for the amount of compression that you must do to the spring so that the block can move, through point B and complete the circular motion, then with friction, you're going to have to press a little bit harder, right? X has to be greater than before because you have to have enough initial energy to overcome the negative work done by friction and have enough energy left so the time you reach VB, you still have at least the minimum speed that's required to complete the circular motion. Okay, so you can redo this problem without using conservation of energy, but you can then write instead of EB equals E initial, which is what we wrote here. Okay, which is what we wrote here. You can write instead, E initial minus EB equals to the work done by friction. What I should say, E final, which is EB minus E initial. Okay, that equals the negative work done by friction because you find the energy final at point B is going to be less than energy initial because of the negative work done by friction. Okay, so that's going to change the result a little bit, but you should be able to still solve this problem by combining the energy consideration plus Newton's second law applied to point B for the circular motion. Okay, so that is our last lecture for chapter 8, including the work done by non-conservative force. You can think of chapter 7 and 8 as 2 chapters of the same category. We both concentrated on the effect of a force over space, and in doing so, introduced the work energy theorem and its variation, the conservation of mechanical energy, our first of the 3 conservation laws, and you will find them to be highly effective at solving problems. Just make sure you understand the condition for each of the 3 conservation laws. So 1 down, 2 more to go, 2 more conservation laws to go. Okay, and in the next chapter, chapter 9, we're going to switch gears. We're now going to look at the effect of a force over time. And just like we did in chapter 7 and 8, we'll be introducing, again, new concepts and new methods for solving problems when we look at the effect of force over time. So that is chapter 9 coming up.